Okay, let's try to understand how do we have to use properly the transmission lines if we want, for example, to optimize the transfer of power between different elements. Say between, for example, a generator here in the left, we have the transmission line. At the end, we have a load. So let's assume, for example, the load have, for example, the same characteristic impedance of the transmission line, and let's assume for a moment the generator also have an output impedance which is also coincident with the same characteristic impedance of the line and the load. So if everything has the same impedance, there's no problem, because what happens here is this signal, the signal which is supplied by the generator is going to find an impedance which is exactly the same as the generator. As we will see in a future lesson, this means maximum transfer of power is delivered to the line. And when this signal propagates along the line and reaches the end, if at the end we have the same impedance of the characteristics impedance of the line, everything is going to be transferred to the load. There's no reflection, and it's exactly like if we have an infinite line, so there's no return, there's no reflection, and the transfer of power is maximized in this case. But let's assume now a more complicated situation when we have, for example, the same impedance in the generator, the transmission line, but a different termination impedance at the end of the transmission line. What's going to happen in this case? Well, remember what is the definition of impedance. The impedance is no more than a parameter which relates the voltage and the current. Okay? So along the transmission line, the voltage and current along the transmission line are actually described by a factor of a scale which is Z0. This is the characteristic impedance. But at the end of the line, we have a different impedance. What does it mean? Okay, this means that the relationship between the voltage and intensity, in this case of the current, is different to the relationship of the factor of a scale between voltage and current along the line. Then what's going to happen? There's something, this is a mismatch here. So in the left, we have a relationship which is a certain one, which is defined by Z0, and at the right of this point, we have a different ratio. Then what's going to happen? Is this possible? Well, there is only one way to make it possible. There's no contradiction between these two realities if we make a pair, or we actually provide here the existence of a backward, a reflected wave. So if we, instead of considering only a wave which is actually propagated from the left to the right, if we consider now a backward or reflected wave which is propagated from the right to the left, we can actually make this situation compatible, and we can match voltage and intensity, actually match both the left and the right side of this point, of this connection point. So the only way to make this situation feasible or possible is to include not only a forward wave, but a backward or reflected wave starting from the load. In other words, if the line is not terminated with the same impedance as the characteristic impedance of the transmission line, we have a reflection. So let's try to actually model this mathematically. We have here two equations, voltage and intensity equation. The intensity of the current, it is actually here expressed as voltage divided by the characteristic impedance of the line. And if we play with these two equations and we take into account the relationship between voltage and intensity, which is actually existing here in the termination load or impedance, now we can calculate the reflection coefficient, which is the same as the ratio between the reflected and the transmitted wave along the transmission line. And this depends on the termination and characteristic impedance of the transmission line itself. In such a way, if the termination is equal to Z0, then the reflection will be 0. There won't be a reflection in the transmission line. And if the termination impedance is very different from Z0, then we will have a certain reflection coefficient that will be as important as the difference between the impedance of the line and the termination. In other words, if we want to maximize the transfer of power, we have to make this impedance, load impedance, as close as possible to the characteristic impedance of the line. Otherwise, we will have a reflection. Now, what is interesting here is we have defined the reflection parameter at the output port of the transmission line, but because we know how these waves, the forward and backward waves, propagate along the line, actually they are in the lossless case, low loss case of a transmission line, actually these signals evolve along the line with a phase change, which is modeled with this parameter. This means that if we have the reflection coefficient, which is known at one point, for example, at the end of the line with the previous expression, we can also express this reflection coefficient, its evolution along the transmission line. And this is described by this expression. So we have the same amplitude, the same modulus of the reflection coefficient is preserved, and the changes along the line, the only change is a phase. So the relationship between the transmitted and reflected wave is actually suffering a phase change along the transmission line. This is what this expression is telling us. Now, let's take an example. Let's assume the termination ZL at the end of the line is different from the characteristic impedance of the line, so we have a reflection in this case. So we have a forward and a backward wave propagating, shading the same transmission line. So what's going to happen with the voltage, for example, along the line? Okay, we will have the oscillation of the frequency of the signal we are transmitting, but let's take a look at the amplitude. The amplitude is not constant. We have some maximum and some minimum. The maximum will be actually produced by the fact that both transmitted and reflected wave have the same phase, so they reinforce together. Then we will have the maximum situation, maximum amplitude, but at other position along the line, the phase of this forward and backward propagating waves will be opposite, so they will tend to cancel each other. In this case, we will have a minimum. And this situation is static. So if you maintain your generation of power here and you measure your voltage, you will see this is actually propagating, but this maximum and minimum stays statically at the same point. That's why this is called a standing wave situation, when this pattern of maximum and minimum are maintained along the time, are not evolving, are fixed position along the line. That's why this is called a standing wave. And we can define a standing wave ratio parameter, which is actually the ratio between the maximum and the minimum. So for a no reflection case, this parameter will be just 1, because there's no maximum, no minimum, they're both the same parameter. But when we have a strong reflection, there will be a strong discrepancy between these two values, and then this parameter will be much higher than 1. The input impedance, which is also another interesting parameter, can be calculated quite easily if we know what is this load and the reflection coefficient. So what we have to do here is we can calculate what is the reflection coefficient here at the input, and using the same expressions as before, we can translate this reflection coefficient here into impedance, and this is the input impedance at the beginning of the line. So if you have this reflection coefficient and you want to know what is the impedance this generator is seeing here at the input port of the line, this is given by this expression, and it depends on the characteristic impedance of the line, the termination impedance, and also the length of the transmission line and the beta parameters, which is related to the frequency of the signal which is propagating along this line. These expressions have certain applications, interesting applications. So let's assume, for example, We have a termination impedance. In this case, it's a real parameter, a resistor, for example. We know the value of this resistor. Let's assume this resistance is different from Z0 parameter, and we want to obtain here an input impedance which is, for example, similar to Z0. Can we do this? Well, we can do the following. We can, instead of connecting the generator or this line directly to the resistor here, RL, we can actually make a connection through a quarter lambda piece of line. The length of this transmission line here is lambda, the wavelength, divided by 4. And let's actually assume this parameter can be changed. The impedance of this piece of line, this quarter lambda line, can be changed to some arbitrary Z1 parameter. Let's see what happens. If we calculate here the input impedance here at the beginning of the line, we obtain this expression. And then, for the particular case, when the length of the line is lambda divided by 4, then actually the input impedance is this very simple expression which relates the characteristic impedance of the line, and you have here the parameter of the termination resistance at the output port of the line. So what you see here is the input impedance is inverted, is an inverse term. We have this constant, but forget the constant for a moment. It is inversely proportional to the output impedance. So it's not a direct proportionality, it's an inverse proportionality, and this is why this quarter lambda piece of line is called quarter lambda transformer. It can actually modifies with an inverse term here the output impedance and presents an input impedance that is just the inversion of this termination impedance, taking into account the characteristic impedance of the transmission line, of this quarter lambda. This is called a quarter lambda transformer of impedance, because, for example, if you want to minimize reflection here at the input port, so you want to maximize transfer of power along this transformer and termination load, what you have to achieve is a zero reflection at this input port. So in this case, what we want is the input impedance at this plane exactly equal to Z0. In this case, we have no reflection. And can we achieve this? The answer is yes. We have to actually take here the proper impedance parameter of the characteristic impedance of this transmission line transformer. And if we make this the geometric mean of the input and output impedance, then we achieve it. So we can actually make matching of impedance from a load to a generator just by using a piece of transmission line with a length of a quarter lambda and with a characteristic impedance, which is this geometric mean, and then we achieve our purpose. We maximize power transfer to our load.